So today we have the last topic that will be covered. It will be on the test, quadratic functions, and then we have the test. I gave you the review last week, right? Who emailed me about the quizzes online thing? Yeah.
And it shows that, well, I did the quiz that you assigned Monday.
Yeah.
That wasn't a
But there's nothing, but I don't post anything online.
Okay. I
Quizzes.
saw things on the old stuff. And
Yeah.
so,
Okay. So what are we going to talk about today? Quadratic functions? Football. Let's talk about football. Let's talk about the cowgirls. I don't know. Romo looked pretty happy to be on the sidelines injured, if you ask me. That could be it. 4.3. 4.3. Oh, come on. This is ridiculous. Come on. What is this? There we go, finally. Are you all ready? Shall we begin? Okay. So we're going to talk about quadratic functions and their graphs. And there are two forms of a quadratic function. When you see them written down, you should be able to recognize both of them and quickly know which is which. So I'll put it on the board even though it's in your notes because it's so important. All quadratic functions can be written this way or this way. Right. This form here we call the what form? Expanded form. This one is called the standard form. And there is a way that you can go from expanded form to standard form. There is a way that you can go from standard form to expanded form. It's usually easier to go from here to here, because all you have to do is actually square out what this is. So we'll talk more about this. I just want you to see that what the two forms look like. There are some things that are similar in both. The variable in both of these is x. So x is the variable here. There's also one letter that they both have in common. What is that other than the x? The a. They both have this a in common. So whatever a is here would be the same a that's here. And then the b and c are two other numbers, but they are not the same as the h and k. Right? So the numbers here will be different than the numbers there. All right? Just bear with me for now. All right, so now, what do the graphs of these things look like? So what are the characteristics if you graph these functions? They're not lines, right? They're what we call parabolas. We all know what a parabola looks like? What does it look like? Looks like a U, right? Looks like a U. And normally we say it's like a U that goes like this, right? Or it might be a U that goes like this. Then it's not a U anymore. But that's a flipped over U, right? So parabolas, the ones we're going to study, are going to be parabolas that we say open up, right? This would be a parabola that opens up. This would be a parabola that opens down. And there's a very easy way to determine which of these two cases it is. All you have to do is look at that number A that appeared in both versions. As soon as you see that number A, you'll know which of these it is. And it says it there in part 2 of the notes there, that if A is positive, A greater than 0 means positive, right? Numbers that are greater than 0 are positive. Then it's going to open up. If A is less than 0, that means it is negative, then it'll open down, right? And Liz, positive people smile, don't they? And that kind of looks like a smile? Yes? And negative people like to frown? That kind of looks like a frown. It's kind of cheesy, right? But you remember it that way, maybe? Most students have no problem with that part of it, right? Okay. Now, before I continue, why do we study parabolas? What's interesting about a parabola? Well, see if I can do this without hurting anybody. You want to be my volunteer? Yeah, go ahead. Go ahead, you can be my volunteer. All right, so I don't know, you can stand right there. I don't know if the camera's going to pick this up or not.
Please don't hurt me.
I won't. So I'm gonna throw these markers across to Romo over there. All right, and just watch the path of the marker through the air. All right?
Am I catching it there?
Yep, catch it. All right, toss it back. Okay, so the trajectory of this, right, go ahead. Now I'm going to go a little faster. It's going to be not as, okay, so that, there we go. Ready?
Tried to be cool.
All right, so that's it. Here. So what do those look like when they travel through the air? They are parabolas. Okay, it's not kind of a parabola, it is a parabola. All objects, when they travel through the air under the force of gravity, will travel in a parabolic path. Exactly. All right? And because of that, there's been a need to understand parabolas a little better. One of the examples I like to give is, you know, there's been a need, and if you look back in history, please don't get jealous of my art skills here, okay, as I draw this. This is a castle, okay? That's a castle. And if you want to storm a castle and take all their stuff, right? Take all their treasures and whatever you want to do over there. Right? Whatever it is that people like to do to each other, right? Then you could try and get through the castle walls, right? And so maybe you build a catapult, right? And you say, what? You just lob this stuff over there, right? Just hope that it hits, hope that you cause chaos and disorder. Is that the way we still do it today?
Yeah.
Yeah, but now it's not as bad as just throwing it and hoping for the best, right? Now it's satellite GPS coordinates, go right where we want it, right? It's gotten a lot better. But the progression of that, there was a point in time where we understood that, look, just lobbing is no longer acceptable. If we want to hit exactly the target we want to hit, then we need to understand the parabola. I know we have some military people backgrounds here. Artillery use calculations based on parabolas in order to determine where they'll hit. They have to take a lot of things into account, though, wind and atmospheric things and what projectile they're using. But they can launch a projectile and hit something miles and miles away with pretty good accuracy because they understand the parabola. There is some, if you're going to launch a projectile, there is some function out there that looks like this, okay, that will dictate the path of that projectile through the air. Now, determining what it is the challenge, and it can be done. So if I have a parabola, let me show you. Let's have that piece of artillery. Well, let me graph a parabola first. Let's say we have a parabola that looks like this. Then this is where it would hit the ground, wouldn't it? And so as I launch this out of my, whatever it is, my artillery piece, and I go here, what I'm really looking for there is the x-intercept, aren't I? And to find x-intercepts of functions, what do? We take the function and set it equal to 0, or we replace y with 0. Do you remember doing that with lines? To find the x-intercept, you set y equal to 0, solve for x. So if we can come in here and call this function y, then if I just set this to 0, set this to 0, figure out where that is, I can tell you where it's going to hit, can't I? I can actually tell you the distance right here. Yes? So kind of useful to know a little bit about parabolas. It's amazing that technology has come so far, right? A lot of the advances in technology has been a result of us wanting to find more efficient ways to kill each other, right? Yeah. Okay, on that positive note, let me show you a different use of parabolas that's a little less severe. So if you drive a car at night, you turn on your headlights, right? You have like low beam, high beam, right? Things like that. So if you have your low beams, they're aimed a little different. They're not as bright, right? There's certain things about them, but they're all based on the principle that you have a light bulb. So sorry, this is my light bulb, right? And that's in your headlight. And then what they do is they behind it, it's three-dimensional. So it looks like this. Okay, and your light bulb is down in here. I'll just show the edge of the light bulb in there. Okay, so there's a light, and this little cup cone-looking thing is reflective material, right? It's like mirror on the inside, like a mirror. So what happens is the light bulb that's in there, all the light rays that come out, they hit this, and when they hit it, they reflect. And the angle that it reflects at is straight out. So even the light rays coming out the back are going to be like this. The ones that come out here, they will hit and come out. So every single beam of light that comes out will all come out straight, right? And so the shape of this right here, the curve of that mirror, cannot be just any curve. It must be a parabola for this to work. If this is not a parabola, these light beams will come out scattered out like this. And then you don't get a beam of light, you just get kind of like a light bulb in a room. It just, the light goes everywhere. You want to focus that light into one place, you have to have a parabola behind it. Understand? Where to place that light bulb to get this perfect beam, that point is actually called the focus. And so knowing where to place that, again, you need to know the function that you're using in order to find that focus. Any of you ever use one of those lights, those like mag lights where you turn it and the beam goes like that? All you're doing there is moving the mirror back and forth. If you move the mirror back or forth, it'll either widen the beam or narrow it. That's all that you're doing. Sometimes you're moving the bulb, but in either case, one of these two things is moving. All right, so one more thing that parabolas are used for. It's the opposite of this right here. We all use our cell phones, right? You sit there and how do we connect to, when we make phone calls, we connect to there's like little, out on the roads, on the side, there's some little pole with some tower, right? With some signal processor up there, right? But yeah, what do we do when we're trying to connect very, very far distances, like the other side of the world? What do we use? Like if I'm trying to communicate, here's me, right? And I'm trying to communicate with this guy over here, right? I can't possibly have a tower that would relay another tower to another tower to another tower to another tower. It'd take a lot of towers, wouldn't it? And there's ocean too, so how do you get across the ocean? So what do we use? Satellites, right? So how does a satellite work? We send a signal out, right, over here. So I send my signal out, and I don't even send it out to a certain place. I just broadcast it everywhere. And then up here in space, there's a satellite. It's got this little dish-looking thing, right, with this little that thing, that's sitting there. You know what I'm talking about? Okay, so there's my little satellite dish. And what is it doing? Why does it have that shape to it? But why does it, you've seen these on people's apartments, right? Or on their houses on the side, like clipped to the side of their house, these dishes, right? Dish network. That's right. This dish right here is a parabola, and it's the opposite of the flashlight. So as it's sitting there looking for a signal, every single signal, even if it's very, very weak, will come in here and it will reflect exactly to that focus. Every single little weak signal. And when it gets to the focus, all those weak signals become amplified. And so at that point, you're picking up a good signal. And then that's where you watch your TV or whatever. Or if it's a signal you're sending across the world, you send it here, then there's another satellite over here listening, and it's going to pick that up, and then it's going to send it back down. So you can get around, send a signal at the speed of light around the world using that dish. But you have to use a parabola. There's no other way around it. So they're kind of useful. All we're going to do in this class is just learn how to graph them, learn how to manipulate them, and then the engineers would move on and study them more and use them to build something, right? All right. That didn't seem to get any of you very excited. All right. Okay, so back onto the parabolas. We had the two versions of them here. I'm just going to put the two versions. We have a very important point that appears on both of the parabolas. On a parabola that opens up, it would be the lowest point. On the parabola that opens down, it would be the highest point, right? So this would be like a local minimum and a global minimum, wouldn't it? And this would be a local maximum and a global maximum. That point is called the vertex. I realize a lot of you have already seen parabolas, all right? But I'll talk about it anyway. And that point is so special that we don't just call the x and y coordinates x and y, we call them h and k. To really let somebody know, look, that is an important point. That's the vertex of the parabola. So we label it hk instead of xy, all right? All right, all parabolas have an axis of symmetry. An axis of symmetry is a vertical dotted, well, it's a vertical imaginary line. It's not part of the parabola, but if we look at this vertical line right here, that vertical line splits the parabola in half, and the parabola is symmetric there. So reflection like this. And that vertical line has an equation y equals k. I'm sorry, h. Y is h. It's always the x value of the vertex, right? The left and right. That will always be, where's my brain? It's Monday. X is h. Look, it was a good weekend. It was a long weekend, all right? Give me a break. It's my first class. All right, x is h, right? X is left and right. H is this coordinate. So wherever that is, wherever that point is, left and right, that's where that vertical line will be. It says it right there, too. All right, what's the domain? The domain is all real numbers. We can see that the graph extends out to the left and to the right forever. It's, going out. Same thing up there, it's going out. So domain's everything. What about a y-intercept? Does a parabola have to have a y-intercept? Yes or no? So let me draw an xy axis. Is it possible to draw a parabola that does not hit the y-axis? A parabola that opens up or down. Can't open sideways. What do y'all think? I'm seeing some yeses. How would I draw it where it can't hit the y? But that wouldn't be a parabola then. See, remember, the parabola has to open up. As it goes out, it has to keep going out. Or if it goes down, it has to keep going out. So it would be impossible to draw it without it hitting the x-axis. I mean, the y-axis. So look, if I go here and start drawing out like this, eventually, even if you make this really, really narrow like this, right? You may say, no, it's not going to hit. Well, eventually, if it's a parabola, it has to keep going. So as it moves down, it moves out, and it will hit the y-axis. Understand? So you have to have a y-intercept always, which means if we're graphing these, we should always try and find that, shouldn't we? I mean, it'll always be part of the graph. So what we're trying to do is create a list of things, characteristics of parabolas that we should be able to get and then graph. Everyone agree that the vertex would be a pretty important point to know? That would give us kind of a starting point with our graph. And then if we knew a y-intercept, that would give us something else. How about x-intercepts? Do we have to have x-intercepts when we draw parabolas? No, you do not. Can you have x-intercepts? Yes, but you don't have to. So here's an example of a parabola that would have no x-intercepts. Right? Is it possible to only have one x-intercept? Yes, the vertex would have to be what then? On the x-axis. So here's an example of a parabola that would have a single x-intercept. And then, of course, we could have two, couldn't we? Parabola that did this. So with all parabolas, you're either going to have two x-intercepts, one x-intercept, or no x-intercepts, right? Is it possible to have three? No. It's impossible. So that's what the note says there. X-intercepts may have two, one, or none. All right, so let's practice now. I'm going to give you an example of a parabola. I'm going to give it to you in standard form, and then we're going to try and get it into the expanded form. Then we're going to get to graphing. So your first example is the function f of x equals -2 in parentheses x plus 3 squared plus 8. The instructions here are to convert this from standard form to expanded form. Do we all agree that this is in standard form? Yes? Okay, if you agree with that, then you can tell me right now, even though it's not part of what I'm asking for, if you think this is in standard form, then you should be able to tell me what A, H, and K are, just by looking at this. So be careful here. What's A? -2. What is H?
-3.
It's the opposite of what you see here. Because in the formula, back up in the formula, it had a minus in the parentheses there. And so that gets a little tricky. So I would just tell you that x plus 3 is x minus -3, isn't it? That's what that is? So you could say, oh, that's x minus -3, so h is -3. Or you could just be like, look, anytime I see this, I just take the opposite of the number I see. If it's plus, I'm going to put a minus. If it's minus, I'm going to put a plus. So -3? Yes? K? What about K? K is actually what you see. So 8? All right, so we have a standard form. This is a parabola. I know quite a bit about it already, don't I? But I want to get this into standard form. So to convert it to standard form means we really just need to remove this parenthesis right here. Because in the standard form, you don't have that parenthesis, do you? So let's do x plus 3 squared. What is x plus 3 squared? I'll do it on the side here. So x squared plus 6x plus 9, that's what that is? But what's sitting in front of it? -2. So that -2 must distribute to each of those terms. So this becomes what? -2x squared, -2 to here, minus 12x, minus 18, and then what did you still have here? Plus 8? And then just -18 plus 8 is -10. That is in standard form, isn't it? For standard form, instead of having A, H, K, you actually have A, B, and C, right? So tell me what A, B, and C are here for standard form. A is -2. Same as this, right? Should be always the same. But B this time is different than H and K. What's B? -12. And then C is -10. Understand the difference? But if you were to graph these, okay? If you were to take this parabola and graph it, it would be exactly the same as this parabola. They look identical. So, you might be asking, well, why have two different forms? Well, sometimes it's easier to work with this one. Sometimes it's easier to work with this one. It depends on what you're trying to do, as you're going to see as we move on. Questions? That's a good question. I'm pretty sure that's what we're going to do next. Now, there are different ways to do this. So I think what I'll do is, let's do the same problem, okay? That way we know what the answer is supposed to look like. Let's start with this. And let's convert this into standard form. We know what the answer is supposed to be, right? At the end, it should be what? -2 and then parentheses, x plus 3. Well, factoring it, if it factors, does that factor? Yeah. So look, let's take a vote, okay? I'll let you, this will be a totalitarian democracy. You know what that is? I let you vote, I listen, but it doesn't matter. I'm going to make up the decision anyway. But let's vote. How many of you want to see this done the algebraic way that requires more math that may be beneficial later, or versus the shortcut way? So,
Does a shortcut always work?
shortcut would always work.
Why are you asking? You know the answer.
No, I want to know what you want. I'm curious.
Which one is complete? All that.
Completing the square is the harder one. You want to see it? Okay. So it's called completing the square. I'll show you the shortcut method after this. How many of you have done completing the square before? Okay. Please pay attention to this, especially if you're going to take calculus, all right? Because I get Cal 2 students that still don't know how to do completing the square properly, because they're taught it a certain way and there's something wrong with the way they're taught it. It's dangerous, all right? I'm about to find out how many of you know it a certain way. We're going to see. All right, so for completing the square, first of all, you have to have a standard form parabola. That's what we have. And then, does anyone know from completing the square what the first step is for completing the square? Set it to 0. That you can't do. No, that's not it. Okay. No, okay, but that's what a lot of students do. I don't know if you were just kind of...
I think that's how I was taught.
Yeah, the problem with that is that this is an expression, not an equation. Okay, but look, first step always, all right? First step always is to make sure that the leading coefficient on the x squared term, and I am assuming you have it in descending order first, all right? So it has to be in descending order. But you have to make sure that that number in front there is a 1, which it's not. So a lot of students are taught divide by -2. We don't have an equation here. We cannot divide by -2. The only thing we can do is factor out a -2. So what I'll do is I will pull a -2 out, leave me with x squared what? Plus 6x plus 5. Okay, are there any questions? Remember, our goal is to get it to this, right? That's our goal? That's our goal, okay. Now, this factors, maybe, yes? But that does not matter. That's not completing the square. Completing the square has nothing to do with now trying to factor this. Does anyone know the next step for completing the square? Okay, good. You take the number, not the x, just the number in front of x. And if it's negative, you have to look at it as negative. Here, in this case, it's positive 6, right? What do you remember what you do with that number? You take the positive 6 and you divide it by 2. Always 2 when you complete the square, right? Always 2. And that gives you 3. And this right here is going to be a special number. That's a star, okay? That's a special number. I'm going to use that again in a minute. Then, after I get that answer, I'm going to take that answer, whatever it was, and I'm going to square it. And I will always do that every single time I'm doing completing the square. And that'll give me 9. And that's my second special number, which I'm about to use again. All right, so from the completing the square, after you've pulled the 2 out, and you've got this, you look at this number, you take half of it, put it aside, you take that half thing you just got and square it and put it aside. All right? Questions? Does this look familiar to some of you? Okay. Now, -2 x squared plus 6x. Anybody know what to do now? This is the part that, okay, the 9 is the number we're going to use first, right? What do you do with it? Add it? Yes? Just add it? Where? Where do I add it?
I'm assuming right after the 6x.
Right after the 6x. So how many of you have heard, or remember completing the square, you were told you just add 9 to both sides? Something like that? Did it ring a bell? No? Okay. Again, you have to be careful here. We don't have an equation. You cannot add 9 to both sides. We're saying f of x equals this, f of x equals this. So what I'm going to do, and this is going to be something that as you move through mathematics and you do more, you'll see this very, very nice special thing I'm doing. I'm actually realizing, don't write this down, I'm realizing that right next to that 6x, between the 5 and the 6x, there's a 0. Right? And you can write 0 infinitely many ways. In fact, you could write it this way, couldn't you? Instead of 0, couldn't I put 9 minus 9? Right, that number? 9, and then take 9 away right away, and wouldn't that still be 0? And then I have plus 5 out here? Does everyone agree that's the exact same problem? Now, why I do that is about to be illustrated in the next step. So after you find these two numbers, you take this one, you go right past your x term, you add it and subtract it. You don't subtract it and add it, you add it and subtract it. All right? These first 3 terms right here, first 3 terms right there, are guaranteed to factor. Guaranteed. By design, the way this thing works, those will always factor. Not only will it factor, it'll be a perfect square trinomial, meaning whatever this factors to be, it's 2 of the same exact things. What are they? X plus 3 times x plus 3. Isn't that how that factors? X plus 3 times x plus 3. But you actually don't even have to know that, because that number tells you what it would be. Okay, so this right here is guaranteed to factor to be x, and then whatever this number is, if it's positive 3, I put plus 3, times itself, which is squared. Understand that? See that? I still need to write the negative 2 out here in front. What's still back here, though?
Minus 9 plus 5.
Minus 9 plus 5, which is minus 4. But didn't I have a negative 2 sitting in front of all of this? Yes? So I'm going to put a negative 2 here. And to really make sure you understand, I'm going to put a parenthesis or a bracket. Those are the same thing in math. It doesn't matter. Right? So that's my expression. You with me? Last step is to take the negative 2 and distribute it here, which means I'm just going to place it right in front of this parenthesis and take the negative 2 and multiply it times the back. And what would you get if you do that? Yep. Negative 2 in parentheses x plus 3 squared plus 8. And isn't that what we wanted? Yes. That's it. It's a hidden 0 right here. This is what we call a hidden 0 in math. We create a 0, a special 0, that makes things work exactly the way we want it to work, and it's called completing the square. All right, so we can go back and forth. You want the short way now? All right, the short way is a gift. It is a gift from Calculus 1. All right, you take Cal 1, you can prove this very easily. All right? And I think I can even kind of get to the idea. Do you remember I talked about the difference quotient? I said the difference quotient, the idea was that it gave you the slope of the line between 2 points. Do you remember me talking about that? But in Cal 1, we want to move one point closer to the other. Yes. Remember that? So tell me about this. This vertex right here, okay? That vertex, the highest point on the graph. If I were to take another point and find the slope of this tangent line, the slope would be what, negative? Yes. Now if I move that point right on top of that point, what is the slope of that line? Yes, it's flat, isn't it? The slope of a flat line is 0, isn't it? So if you do the difference quotient on the parabola and set it equal to 0, which would be this slope, you would actually get the formula I'm about to give you. But it's beyond what I want to do in this class. It would take me about 20, 30 minutes to do. So I'm not going to do it. But in Cal 1, you would. And that's where this formula comes from. Right? I don't want you to think that it was on the back of some stone tablets that were found behind some bush or something like that. And here are all the formulas in math, you know, like, right? Know what I'm saying? Okay. What's that?
It's like the Ten Commandments with the math formulas.
Yeah, there's one version of the story where there's like the 10 Commandments, and then there was like another set of tablets that had all the math. I'm kidding. I'm kidding.
I missed that one.
Yeah. All right, so there we go. Starting here, ending, we know where we want to end, right? So here it is. This is kind of the no worries, just here's the formula, use it. All right, here it goes. You want to know what h is, because remember, we want this, right? We already know what a is, don't we? We just need h and k and we're done, right? Tell me what h is, tell me what k is, and I'm done. Well, I'll tell you what h is. It'll always be negative b divided by 2 times a. Always. So what is negative b for us here? Positive 12, opposite of what I have. And then 2 times a, 2 times, what's a? Negative 2. What is 12 divided by negative 4? Is negative 3, right? H is negative 3. And when I plug it in, it becomes positive, yeah. But I still need to get k, right? I need to get k. All right, so k, there's a formula for k. All you do to find k is take the h you just got and plug it into the function. So you take this answer, negative 3, and now plug it in for x, and whatever comes out of that, that's k. So I'm going to have, for this particular problem, this is f of negative 3, which is negative 2 times negative 3 squared minus 12 times negative 3 minus 10. And when you do that, you should get, what, 8? Is it 8? Negative 8. I don't remember.
I'm guessing it's positive.
Is it positive? Yeah, because this is 36, right? This right here, you square that, it's 9 times negative 2. It's negative 18 plus 36 minus 10. Yeah, so it turns out to be 18 minus 10, which is 8. So get 8. That's it, we're done. No completing of the square. This is negative 2. X minus negative 3 becomes plus 3. That quantity squared plus 8. Done. I don't have a preference on how you do that on a test. I like the shortcut, but everyone here should be capable of completing the square. Questions, comments, concerns, gripes? All right, so what are you going to be asked for on the test? Really, what I want to know is that you can graph a quadratic function. That's the minimum of what you need to be able to do. And you need to be able to graph a quadratic function irregardless of its form. So if I give it to you in standard form, you should be able to graph it. If I give it to you in expanded form, you should be able to graph it. Either way, all right? So there are a set of steps that I like to give students. Hopefully you like steps. But there are a set of steps that I would recommend you use to graph a quadratic function. There they are. All right? They're in your notes. Now, the reason why I like steps, I don't do it because I want you to be like a monkey where you're like, do this, then this. I mean, I want you to think through things. But these processes that we're going to start to get in this class become kind of long. After we graph parabolas, the next thing we do after this test is we graph polynomial functions, and then we graph rational functions. And those functions, those processes or steps are like 2 or 3 times longer than this. So you may as well get into the idea that you're going to be doing something that takes you 30 minutes to get to the answer, because that's the way it's going to be as we proceed. This one's not so much, but all right, so what's the first step according to what I put here? Make sure you're looking at a quadratic function, all right? Make sure that what you're trying to graph is quadratic. If so, the next thing I recommend you do is you determine if it opens up or down. And you know what, let's actually do this example, the one that we've been messing with. Let's just do this one while we go through the steps. I've already forgotten what it is. All right, so step A would be, do I have a quadratic function? Yes, I have, so I'm just going to put a check mark. A, I've got a quadratic function. What form is it given to me in? It's expanded, right? So this is going to be an example of how to graph an expanded form quadratic function. Next thing, part B, determine if it opens up or down. Which way does this one open? Down. Opens down because A is -2. Right? Liz said that negative people like to frown, right, Liz? What's that? No, I know you're not bored. I know that you're really enjoying this, and that's just your normal look. How do I tell it's down? Oh, because it looks like this as opposed to being like this. Right? The thing that'll give away the standard form a lot of times is that parenthesis. All right, C, let's see, find the vertex. And I put here, to find the vertex, this might require completing the square or the vertex formula. In this particular problem, because it's an expanded form, I actually am going to have to work for this, aren't I? I'm either going to have to do completing the square or I'm going to have to do the vertex formula. Vertex formula, what do I mean by vertex formula? That h was negative b over 2a, k was f of h. Okay, I didn't call it that when I put it on the board. That was the shortcut way. All right, this next step is something that I don't normally see in textbooks. I don't know of anyone else who does it this way. It's just the way that makes most sense to me. I ask you at this step to do an actual quick sketch. Okay, so at step D, quick sketch. Wait, are we going to find the vertex? Do you want to do that now? Okay, all right, let's do the vertex. So how would we do the vertex here? We already did it just now, right? We just did this? So look back in your notes. What did we get? H was -3 and K was 8, right? C, work. You just did this problem, right? Part D. Now a quick sketch. So when I say quick sketch, I mean quick sketch. I don't mean come here and get your ruler out and start making all these little marks. Just a real quick x, y axis, and I want you to start with your vertex. Where is your vertex? Left 3? Up 8. So somewhere over here? Yep. Which way does this parabola open? Down. So it goes like this and like this, right? Maybe it's not exactly like that, but it goes down. What can you tell me from this picture? It has 2 x-intercepts. Guaranteed, right? You can guarantee me 2 x-intercepts. I have 2 x-intercepts. Now, here's why I like to do the quick sketch instead of just going and trying to find x-intercepts first. What if this parabola had opened up? You would have none. So why go find something that try and find something that doesn't exist? Understand? This could save yourself some time by just having a quick picture. You with me? Okay. Part D, do a quick sketch. Determine the number of x-intercepts. If you have x-intercepts, set the function equal to 0. This might require factoring or quadratic formula. If you don't have any x-intercepts, we move on. But I do have x-intercepts, right? So since I do, I have to set the function equal to 0. All right. So now, finding my x-intercepts, I take my function -2x squared minus 12x minus 10, and now I set it equal to 0. At this point, you are free to solve that however you want. But I say up there, you might have to factor it. you might have to use a quadratic formula. I'm going to factor it. I pull a -2 out. I got this. And the reason I'm doing factoring is because remember when I pulled the -2 out when I was completing the square earlier? And I said, does this factor? And we said, yes, it did, but it didn't matter. In completing the square, that's not what we were trying to do. But now I know I can break that down. What is it? X plus 5, x plus 1. And now what you do is set each of these factors equal to 0. What about the -2 out front? Do you mess with that or no? What do you do with this -2? Is this an x-intercept? Do we have an x-intercept at -2?
Oh, no, -2 equals 0. Set that equal to 0 too, don't we?
When you have things multiplying to be equal to 0, you're supposed to set each of these equal to 0, right? Can -2 ever be equal to 0? No. Really, this constant, you just divide through by -2. And doesn't it just still stay 0? I just don't want people, because this happens, people will actually think that -2 is an x-intercept. You have to have a factor that has x in it for it to have a solution. So you only have 2 answers here. What are they? -5 and 1. So y'all can set each of those equal to 0, right? Did I say 1? -5 and -1. Yes? So my x-intercepts, if I write them as points, it would be -5, 0, and -1, 0. Those are my 2 x-intercepts. So my graph wasn't that great, right? I mean, this one was on the wrong side, but it's okay, because it was just to let me know I had 2. It's just my quick sketch. All right, done with part D. Part E, find the y-intercept. Y-intercept is usually one of the easier things to ever do for a function, because instead of setting it equal to 0, you're replacing x with 0. You're plugging 0 into the function. Much different calculation. So I'm on step E now. I'm finding the y-intercept. So I'm finding f of 0. So just replace all of these with zeros, right? All of these with zeros. So what happens when you do that here? It's just that -10, isn't it? Is that -10? If it's in expanded form, think about this for a second. If your quadratic is in expanded form, that's expanded form, isn't C always your y-intercept? Because if I replace x with 0, it always kills those off. So in standard form, C is always your y-intercept. All right, so we've got -10. So as a point, the y-intercept is 0, -10. And now it's time to graph. So here's what I expect on your graphs. I don't want you to do this on your graph. Because that's what your calculator screen looks like. Okay? This is unacceptable on the test. Right? I'm not testing to see if you can type this into your graphing calculator. I want a detailed graph of the parabola.
What if that's your graph, but then just boxed it?
That's what the screen looks like on your computer, on the graphing.
Isn't that how you differentiate between all your work and your answer?
What do you mean?
Like you box your answers.
No. I'm literally saying people will just copy their screen off their calculator and give me that as their answer. Like that's what it looks like. No. Let me show you what I want. Okay, I want you to draw an x, y axis. I want you to label it x. I want you to label it y. All right? I want you to think about how far out you need to go on your x and y axes. So where was that vertex? -3, up 8. So you need to go up at least 8, right? Where were your x-intercepts? -5 and -1, right? So you need to go out at least -5. What about your y-intercept? -10. So you have to look at those and get some idea of how much scale you need each way. I think if I go like 15 in each direction, I should be good. So you can do it a couple of ways. You can say 5, 10, 15. You can do that. 5, 10, 15, -5, -10, -15. You know? Then you put your vertex. So I'm going to go to the left 3, right, which is about right there. And up how far? 8, which is going to put me about right there. I will plot the point, and I will label the point, -3, 8. That way everyone knows exactly where that point is. The vertex is where? I'm sorry, not the vertex, the x-intercept? -5 and -1. Label those, -1, 0, -5, 0. And your y-intercept here, -10. So that's the point 0, -10. And then you're going to draw right there a parabola that's going to look like a U. It's not going to be a V with a point on the end of it. It's got to have a curve on the top. If it doesn't curve, it's not a parabola. Also keep in mind that you could imagine that axis of symmetry in here. You don't need to draw it for me, but if you do, that's added bonus. You know that your graph should be symmetric to that line. So you try your best, okay? We're not putting a man on the moon here, so we don't need to be too anal about it. Something like that. And try and do the same thing on the other side. Good enough. See, when I look at that, I can see all the information that you got for the problem. I can see that you solved the vertex correctly, you got the correct x-intercepts, you got the correct y-intercept, and that it opens down. Everything is good, right? Some things to be careful with when you're putting all your information together, trying to get your answers, or your final graph. What would you think if you got this? What would you think if you got that? Like you put your vertex, it's here, your x-intercepts here, and your y-intercepts here. Yeah, it looks piecewise. Something's messed up, right? Either your vertex is off or your x-intercepts are off. Something's off, right? What you don't do is this. Try and make it become some weird parabola. I've seen that happen before. So you don't try and fit something that's not a parabola onto your bad data points, right? So that's always a key flag. That's why I like when you graph these, usually if your answer looks symmetric, everything looks good, most likely you did it right. One thing off and it should not look right. All right, do we have any questions? Time is 11:55. All right, let's try. Let's try and graph on one of these and see how difficult these get. That's pretty nice to them. Some of the other things that I ask, you know, what's the domain of this? What's the range of this? Right? So what's the domain? All real numbers. What's the range? -infinity to 8. Right? Bracket. Where is it increasing? Where is this function increasing? -infinity to -3. Where is it decreasing? -3 to infinity. What else? What's the maximum value of the function? So as a point, written as a point, it's the point -3, 8. The actual highest value it ever attains would be 8. So I take either answer there. You could say either answer. You could say 8 or the point -3, 8. So there's a lot of things that could be asked about this, right? Once you've got the graph. All right. Should we do one that's in? Should we do one in standard form? We got about 40 minutes. Yeah, let's do one standard form, then I'm going to do one more in expanded form, then we're going to do we'll do an application. Okay, here we go. Here's my thing. So f of x, I'm making this one up. I think I'll make this one kind of ugly. Wow. It's not that ugly. I saved you a little bit of work there by making that a 20. You all right, Liz? Is this a quadratic function? Yes. What form is it in? Standard. What's the good thing about standard form? What do we... You have HK, right? You have HK. That's the great thing about standard form. You already know that part. Part B, does it open up or down? Down because A is -5, right? Part C, I don't remember what C is. Vertex. Well, you just said that we know it, don't we? -4, 20, right? Opposite of what we see, then the number out here. Man, we're moving along quick, right? Part D, quick sketch. -4, +20, I'm up here. Opens down. Do I have x-intercepts? Yes, I have 2 of them. So that means I need to go find them. And how do we find them? Set it to 0. Set the function to 0. So I'm getting my x-intercepts by setting the function equal to 0. And when you look at this, it's actually not going to factor like the last one did. We got to do something else. So here's where I am. I'm taking for my x-intercepts, what? Sorry. I'm taking -5, x plus 4 squared plus 20. I'm setting it equal to 0. So you move, I already gave it away. Some people will actually multiply this out, like x plus 4 times x plus 4, and then they'll distribute -5 through, and there's nothing wrong with that, but there's a quicker, easier way to do this, and that's just move the 20 over, subtract 20 on both sides. Then divide both sides by -5. X plus 4 squared equals what? 4, positive, right? Because negative over negative is positive. And then anyone know what to do at this point? Square root both sides, right? Take the square root on both sides. Because if you take the square root of something squared, it should just go away, the root squared. So I'm taking the square root of x plus 4 squared, and then I'm taking the square root of 20. But plus or minus, because I brought the square root in, right? Oh, yeah. Yeah, it's 4. Thank you. I'm all excited about doing that, but okay, 4. But plus or minus, yes? And the left side is x plus 4. Does anyone remember what I said about what happens when you forget the plus or minus? No, you don't know. I guess that didn't stick. That's right, you die. People die. Planes fall out of the sky. Remember, buses go off the edge of a cliff, right? Things like that. I guess that didn't stick the first time I told you. All right. So plus or minus 2? Now, this represents 2 different answers, right? Because it's my x-intercepts, and I should have 2 of them. So you got to make sure you understand how to work with this. Just subtract 4 on both sides. Leave the plus or minus in front of the 2. Subtract 4 on both sides. And then just take positive 2 minus 4, which is what? 2, negative, right? And then take -2 minus 4, which is -6. So there's 2 different scenarios there.